Okay, in this video I'm going to be talking about the TNB frames, also sometimes called the Frame frame. This is going to be the tangent, normal, and binormal vectors to, in general, probably a space curve, but I'm going to start a discussion with a particular plane curve that we're very familiar with, y equals x squared, right? So in single variable calculus, we learned that, if we wanted to take the derivative at x equals 1, we were going to get 2, right? Because the derivative of y equals x squared is y equals 2x, and then at x equals 1, then it'd be 2. And that meant that the slope of the tangent line was 2, right? Okay. Now, I'm proposing that we can also write this, this curve parametrically. So if I just said that, say r of t was equal to t and t squared, then I would, have really the same image, okay? Except it's going to induce an orientation, right? So I'll have this parabola, but necessarily as t is increasing, I'm kind of tracing out this direction, okay? And then in the previous video, I mentioned that, for a plane curve, we can find dy dx by dividing the derivative of y with respect to time by the derivative of x with respect to time, and that gave us our slope, and that wouldn't actually make sense in space. I'm going to just do kind of like what the natural thing to do would be here is take the derivative of r of t and just kind of see what we get back. So r prime of t is going to be equal to, well, the derivative of each component is going to be 1 and 2t. Okay. And now if we're talking about the place where x equals 1 to make it the same discussion as this, well, that's going to be the place where t is equal to 1. So r prime of 1 is the vector 1, 2. Okay, so at the point of tangency, what it's saying is I'm going to go over 1 and up 2, which, okay, that does have a slope of 2. Okay, but notice it's just part of the tangent line. And then if I had done something similar, if I'd parameterized this, r of t is equal to negative t and the square of negative t, that's y equals x squared for sure, then I could say, okay, well, it's just going to look same image, but kind of backwards. And as you might suspect, the tangent is going to kind of look the opposite. Okay, so r prime of t is equal to negative 1, and this is going to be also 2t, I think. Hold on. This is equivalent to regular t squared, so yeah, it's going to be 2t. Now the thing is that the point I'm interested in is where x is equal to positive 1, which in this case is going to be where t is negative 1. Okay, so I'm going to say r prime of negative 1 is going to be negative 1 and negative 2. So I'm going to go to the left by 1 and down by 2, which, like I said, is kind of the opposite. Okay, so that's my first point, is that the derivative of a vector-valued function is going to be a vector that is in the direction of, where the path is headed. And it also is going to be in the direction of the orientation of the curve. Okay? And, moving forward, we're going to need, we're going to be interested in getting a unit length tangent vector. Okay, so r prime of t will be tangent to the path, but it could be quite long. In this case, this had length square root of 5. And sometimes it's good for all of our tangent vectors to be unit length for reasons that you will see here in a couple of minutes. I'm really particularly interested in vector-valued functions that have a constant length because of certain properties they have. Okay. All right, so I will define the unit tangent vector to r of t, which is some kind of vector-valued function, is large T of t is equal to r prime divided by the length of r prime. And if you remember back kind of at the beginning of linear algebra, that was how we cooked up a unit vector. Was we took a vector that had some sort of direction it was heading, then we divided it by its length so it became a unit vector. And I'm going to move over here and I'm going to start in on an example. And I'm going to do the same example. I'm going to cook up the tangent, normal, and binormal vectors for this. I think the binormal vector, I'll just find it at a particular point for ease of calculation and speed of this video. But I'm going to just go over there and I'm going to start in on the example. All right, so my example is the space curve 3 cosine t, 3 sine t, and 4t. And what this is going to be, this is going to trace out some kind of spiral pattern where z is constantly increasing with time. And, you know, so it's going to have some circular aspects to it, and the calculation should be pretty easy. So, you know, the first thing I'm going to ask is, you know, can we find the unit tangent vector at the point 3 root 2 over 2, 3 root 2 over 2, and pi? And so the first thing we're going to need is to get an expression for the unit tangent vector at any time t, and then we will, and then we'll plug in, you know, the special time value. And while I'm at it, I think it would be good for me to just point out the easiest way to figure out what the time value is going to be is to go back to r of t, the statement of the curve, and see which one is kind of the simplest at 4t. Okay, so if 4t equals pi, then t equals pi over 4 is the time I'm interested in. Okay. So first I need to take a derivative, divide it by its length, you know, get myself a formula for the unit tangent vector. So I'm going to start by taking the derivative. And that's equal to negative 3 sine t, 3 cosine t, and 4. Okay. The length of r prime is going to be the square root of, I square this thing, that's 9 sine squared t plus 9 cosine squared t plus 16. Okay, I'm going to apply a little bit of trigonometry. I'm going to factor out the 9s, and I'm going to say that's sine squared t plus cosine squared t, which we know equals 1. Okay, so that's going to be helpful. Plus 16, and that's just going to become the square root of 9 plus 16, and that's the square root of 25, which is 5. Meaning that the unit tangent vector at time t is 1/5 of r prime of t. So I'm just going to take all of the components of r prime of t, and I'm going to divide them by 5. So that's going to be negative 3/5 of sine t, positive 3/5 of cosine t, and 4/5. You know, it might be good to just stop and check and make sure that we've got a unit vector here, but I do because I know I'm going to have, you know, 9 25ths plus 16 25ths, and that'll be 25 25ths. Okay. I think now I'm going to need to show you about, you know, why I would be interested in a unit tangent or a function that has a constant length. Wait, no, I did not actually find the unit tangent at t equals pi over 4. Okay, so at t equals pi over 4, the unit tangent is going to be, okay, sine of pi over 4 is root 2 over 2. I might call that 1 over the square root of 2, though, just to make it a little easier. So negative 3 over 5 root 2. Cosine of pi over 4, also root 2 over 2, so that's going to be 3 over 5 root 2, and then 4/5. Okay, that doesn't really care what t is. Okay, so that's my unit tangent vector at t equals pi over 4. All right, now before I talk about the normal and the binormal vector, I need to point out something about curves that have a constant length. So I am claiming that if a curve has a constant length, then it will be orthogonal to its derivative. Okay? So if r of t is a vector valued function, with a constant length, where C is a real number, then R and R prime will sit orthogonal to each other. And a more mathematical way of saying that is that the dot product of R and R prime is going to be 0. Okay, that was something that we saw in linear algebra, was that those were equivalent conditions. Dot product equaling 0, vectors sit orthogonal to one another. So the proof is not going to be very difficult. Okay, I'm going to suppose that R of t has a constant length. For every t. Okay? Then it will be the case that R dotted with R is equal to C squared. Okay? Now I'll let you think about that for a second, especially if you weren't in my linear algebra class. But if you dot a vector with itself, you will necessarily get the square of its length. Okay? Because how we get the length is we square each component and then take the square root. And dotting something with itself is just basically squaring each component and not taking the square root. Okay? So, and if these two things are equal, then their derivatives with respect to time will be equal also. And we know what the derivative of a constant is, right? That's going to be 0. And this, now, okay, I haven't gone through and shown you how derivative splits over a dot product, but it's what you would expect. It observes the product rule just like in the single variable calculus case. So what I'm going to do is I'm going to say, okay, well, take the derivative of the one and leave the other the same. And then add n, leaving the one the same, taking the derivative of the other. Now these are the same thing because it's just the same thing dotted with itself. And that's going to be equal to 0. Now the dot product does commute. You know, x dotted with y is the same as y dotted with x. So I can say that this is 2 of r dotted with r prime equaling 0. I can do that, also associates. And really, if I've got 2 times a thing equaling 0, well, it's the thing that has to equal 0. So this is telling me that r dotted with r prime is guaranteed to be 0, which is what I'd set out to show in the first place. Okay, so the reason I would show you that is because t is a constant length vector valued function, t of t, the unit tangent. It always has length 1, which means to me that t will be orthogonal to its derivative. Okay, and hold on just a second. Lost my green one. Yeah, and so the normal vector, something that's normal to the tangent, there's going to be a whole lot of vectors. I might attempt to draw you this. Let's see. Envision this being a space curve, right? So when it goes up over here, it's kind of like coming in front. It's not actually self-intersecting. It's going and then it's coming, twisting towards us here. If we took the, hold on, I need more color. I'm going to put in the unit tangent in pink. And, you know, I am assuming this orientation like the way I drew it. And so up here at the top, you know, that might be my unit tangent. And the way that the unit tangent is changing, you know, the derivative of t is going to be orthogonal to it because of this over here. And what we'll do is we will actually call this the unit normal vector. And I think that, you know, pretty sure it's going to look like this. Because it's going to actually point towards where t is heading, if that makes sense. And I'll have more to say about what t, n, and b actually kind of represent in terms of the motion of the object right at the end of the video. So now I'm going to define the unit normal vector. Unit normal to r of t is n of t equals t prime divided by the length of t prime. Now I'm just going to mention that the derivative of a unit vector need not necessarily be, or the derivative of a function at a place where the function is a unit vector, that's not necessarily going to be a unit vector, as you'll see over there in the example. Okay, so in order to get the unit normal, what we're going to do is we're going to do pretty much the same thing. We're going to take the derivative of the tangent vector, we're going to divide it by its own length to make it a unit vector, and that will be a normal vector because of what I showed you over there, that theorem. Okay, so I think now I'm going to jump over to the example, and I'm going to find the unit normal for that helix at the point where t was pi over 4. All right, so if I'm interested in finding the unit normal vector at t equals pi over 4, what I'm going to do is I'm going to go over here, I'm going to take the derivative of t with respect to time, and that will be, okay, negative 3/5 of cosine, negative 3/5 of sine, and 0. Okay, and this, I mean, it's not going to start at the place that you would typically think about when you're thinking about the unit circle from trigonometry, but this is going to be a circle centered around the origin with z equals 0 and radius 3/5. So I don't think, and if you wanted to, you could square all of these components, add them together, use sine squared plus cosine squared equals 1, and come to that conclusion yourself. But I'm just going to claim that the length of t prime is 3/5. So, since we know that the unit normal vector is kind of like, well, t prime divided by the length, so I just need to divide everything by 3/5. Okay, so it's really 5/3 of all of this. But those are actually really convenient. So it's just going to be negative cosine t, negative sine t, and 0. That's super convenient. Okay, so at t equals pi over 4, n is going to equal, negative cosine is going to be negative 1 over square root 2. Negative sine, same thing, negative 1 over square root 2, and 0. Okay. And if you were interested, you could check and verify that these two things dotted to 0. And they do, right? The tangent vector and the normal vector are orthogonal to each other. You can kind of see that's a 0, and these will be opposites. Okay, so that's good. And then, I'll come back here in a second, and I'll calculate the unit binormal. All right, now the last thing I want to define for you is the unit binormal, which is probably, not the most useful thing ever, but it does kind of complete this situation here. I'm going to first define for you the unit binormal. Is given by b is equal to t crossed with n. And that's one thing that we know about crossing two vectors is that it's going to give us a third vector that's mutually orthogonal to the two that we crossed. I also know that it's going to observe the right-hand rule. Now, I had an idea while it was paused that I could, kind of do a little bit of erasing and give you a little more perspective on this thing. I don't know if it's showing up on camera, but it looks a little better that it's going and it's coming in front, okay? Now, if that's the case, then, and also we know that the cross product observes the right-hand rule. So if I cross t with n, the binormal is actually going to come out of the board. And so what I'll do is I'll just kind of draw it, about like that, and it's like that. And kind of what I have to say about the TNB frame is that it does create a new basis for R3. It does create an orthonormal basis for R3, made up of vectors that are relevant to the, motion of an object or a curve or something. It's basically, a new basis that's relevant to the situation that you're interested in. Okay, and now I think I'll wrap up by going over and actually computing the binormal vector. Okay, now for the most part, you can cross t and n in general and get an expression for the binormal vector at any time t. But for now, I'm just going to find the binormal vector at a specific time value because it will be much quicker to compute. All right, so what I know is that b is equal to t crossed with n, right? So I can say this is going to be the determinant of I, j, k, and let's see, t is negative 3 over 5 root 2. Oh, man. Positive 3 over 5 root 2 and 4/5. Now, I need to be very careful about copying this. I'm actually re-recording this video a day later because I made a copy error right here, which made the binormal vector parallel to the normal vector. And we know that's not true. We know they need to be orthogonal. I was just checking the video to make sure I didn't do anything stupid like that. And sure enough, I did. I just made a sign error on copying, and then it pretty much ruined the whole example. So negative 1 over the square root of 2, again, negative 1 over the square root of 2, and 0. Okay, so I can take this determinant. I'm going to cover up I. It's going to be 0 plus 4 over 5 root 2. Okay, I'm going to just write this one vertically. Okay, so it was, 0 plus 4 over 5 root 2. Okay, minus j times, okay, so it'd be 0 plus 4 over 5 root 2. Plus k times, okay, so this one is going to be, hold on. So it would be positive minus a negative. So it would be double whatever I get when I multiply these together. So I've got 3 over 10. So it would be 3 over 5. And I'm going to just double check that real quick. So I've got 3 over 10 minus negative 3 over 10 would be 3 over 5. All right. And sure enough, yeah, this is going to be orthogonal to this one, and it will be orthogonal to the tangent vector. Okay, so that feels right. Okay, I think that's, oh, no, that's not all I've got for you, but I'm going to actually just pick you up and move you back over here. The last thing I had to say, or I said yesterday, was something I'd seen on a YouTube video somewhere. And I was kind of always good with this concept of t and n, but I never heard about this this kind of like distinguishing between n and b. So definitely we can see that t is the direction that the curve is heading. Okay. Okay, n pretty clearly represents, you know, like how that's changing. Right? It's t prime. So n, whoops, is how the curve is turning. And then b is how that curve, while it's turning, is somehow twisting. Okay? I thought that was interesting. And now the difference between turning and twisting is somewhat subtle, but there is a difference, and that is kind of what we're getting at here. And you know, while I'm at it, I'm going to just plug some other YouTube videos. If you just kind of search TNB Frame and look for one where there's animation, there's going to be some curves where they'll show you what the TNB frame looks like as you move along the curve. And I think that that's actually the most useful thing. The technology exists for us to animate these things. I can't draw them very well. I can try to explain to you or draw still images, but you can go and just hit the search bar and get yourself something really nice. I kind of in the past had always thought of, okay, yeah, t is the direction it's heading, n is the direction where t is heading towards, and then b is just like, it just fills out the space. So, but I like this better. Okay? And I think that's all I got for you for this video.